Hello, everyone. Good evening. Uh, Thanks for joining this webinar. Uh, Sorry for the delay. There was some technical glitch, so we fixed it and we're ready to go. So today's webinar topic is on modeling HVAC systems in buildings AI. Before that, just message or a chat in the chat. Just confirm if you're able to hear me. Am I audible? Is the audio clear? Okay. Aditya, can you hear me?
Yes, Praveen, you are audible.
Okay, thanks. So we are good to go. So today's speakers, myself, Praveen, I'm the product marketing manager in Buildings Air. I have around 20 years of experience in multiple disciplines like CFD, simulations, and applied to building HVAC. And so now I'm into product marketing. And with me, Swapnil Lindorkar, he is the BU head of Buildings AI. He has a long history of simulation work experience as well, in particularly in buildings. And we have with us Aditya Ruikar. He's the product manager in Buildings AI. So with that, I'll jump to the agenda of today's webinar. So first, we'll see what is the role of HVAC systems in load calculation and energy modeling. And there will be a short overview or introduction to Buildings AI, our building energy performance software platform. And then we move on to modeling HVAC systems in buildings AI. So we'll cover in detail what are the different HVAC systems, what are the workflows, and we'll go in detail all the HVAC systems supported, the inputs, how can you set up the problem using buildings AI. And then we'll end with the question and answers. So if you have any questions, please post it on the chat box. We'll answer them at the end. So I'll start with this. Yes, the biggest problem is the carbon offset or carbon emission. So the biggest contributor, if you see, buildings play a major contribution, both operations and construction side. Operations mainly in energy consumption. So within building energy consumption, if you see, HVAC is the major contribution. Almost 48% of the building energy consumption is by HVAC. So if it is very critical to rightly size the equipment, select the equipment as well as size the equipment. So because it both contributes in energy consumption and also affects the thermal comfort. So that's why it is very important. And I'll start, the role of HVAC in HVAC modeling HVAC systems, specifically in load calculation as well as energy analysis. So to understand that, we need to understand cooling loads, different components of cooling loads. So one is the conduction, through conduction from roof, exterior walls and windows. So the rate of heat entering into the space through conduction, and solar radiation through window glasses, and conduction from ceiling, interior partition walls and floors, and infiltration air entering into the space through leaks or gaps in the windows, doors, and small cracks in the envelope. And internal heat gain includes people, lights, appliances, equipment, etc. And then there is, ventilation, the outdoor air that we deliberately or intently bring into the space to in order to keep the air, maintain the indoor air quality and keep it ventilated. So that also adds to the coil load, and the system heat gain through fans and other duct leakages. So system heat gain we'll see in detail because that is relevant to the current topic. So under system heat gains, there could be, multiple things. So I'm specifically focusing on showing some examples. So for example, heat gain from a fan. So in your HVAC system, when I say system heat gain, it's HVAC system. So heat gain from the fan and the motor. So it is calculated based on the power input to the motor and then the motor efficiency. So that impact that in fact affects the that in fact add heat to the incoming air. Okay, so depending on the position of fan, even the position of air, whether fan, whether it is before the cooling coil or after the cooling coil, like blow through or draw through. So that also affects the supply, either the supply temperature or the cooling load, cooling coil load. Okay. So another system heat gain is heat gain through duct works. So there could be heat transfer from the plenum area to the duct. So they have been insulated and return ducts if it is open return or ducted return. So depending on those things, also the heat load will the equipment sizing will be impacted. So that needs to be modeled perfectly. And in case of energy analysis, whether you select the CAV system or air handling, like air systems with plants, the chiller efficiency, heat pump efficiency. So everything, whether it's a variable frequency drive. So all these things you need to specify. So only then you will be able to mimic the exact system in reality, and you will be able to predict the whole energy consumption for the year. So with that, we'll jump to the introduction of Buildings AI. So Buildings AI is an agentic AI platform for HVAC load calculation and building energy modeling. So it is powered by Energy Plus engine in the backend and Autodesk platform services for the different services, like for example, viewing the model on the web platform and stuff, and then AWS for cloud, computation. So recently we have launched this platform in the month of February in HR Expo, and then we have been onboarding early access users from different organizations across the world. So far, around 100 plus users have joined, and we are interacting with them continuously to get their feedback and improve the product for features further. So how it works? The input involves the project data, the site location, weather data, the building type, whether it is a commercial, residential, under commercial, what are the office space or hotel, that kind of information. And then standards which you want to comply with. The building data includes the building model itself, and then the construction set, the material part, and the zoning part for HVAC, and then the schedules of people, like all the internal load, like lighting load, power, infiltration, ventilation schedules, and set point schedules also, depending on the need for the space. And then the HVAC data, which is the air system related data and plants related data. So this is our focus. This will be our focus today. And so when you feed all these inputs into the platform, it generates the load calculation report and energy analysis, the reports and insights as well. So with that, we'll jump to HVAC system modeling, how we will be able to perform the HVAC system modeling. For this, I call Swapnil to take over from here. Swapnil, over to you.
Hello everyone. I hope my voice is audible. If anyone can just confirm.
Yes, yes.
Okay, so welcome everybody to this. I think this is our second among the series of webinars that we are conducting for Buildings AI, which is our platform for heating, cooling, load calculation, as well as energy modeling. So I am not sure how many of you are attended our previous webinar as well, but in that we introduce uh, our platform, how it works along with a case study. And what we now aim to do through a series of webinars is basically show different features, how easy it is to model, expose some of the user-friendly setup workflows in our platform. And this is first among them, where we'll explain how our pre-configured HVAC system setup can help you to quickly assign basically your systems to the zones that you are modeling, to the building setup, and proceed with your energy as well as the HVAC systems simulation. So overall, this is a short introduction to the workflow. Now, this is how our basically the HVAC configurator panel looks like, which we call basically a workflow, which assigns your HVAC system, required HVAC system to the geometry or the zones. So if we start with initially, we have three methods to basically assign HVAC system to the building model. First is the ideal air system, which is just like which is just a way to basically counter the heating or the cooling load within the system. It doesn't involve any components or any HVAC practical HVAC system as such. It just compensates for the heat or the cooling loads, and you can quickly size up the overall building system. The second one is basically the pre-configured template HVAC system, in which we have a list of pre-configured systems, even on the air handling side as well as the outdoor or the secondary coolant side. And you can just assign those systems to your geometry or your zones, and you don't need to make any complicated system diagrams or anything. These are commonly used systems that are available. This is the second one basically. And when we call what we call the third one is basically custom HVAC systems, which is for advanced users. They can actually configure their HVAC system using our HVAC canvas. But I think this will keep for the second, like for the next series of webinars. So the current one which we are basically focusing in this webinar is the template or the pre-configured HVAC system. When you enter into that, you can basically select your zones to which you have to apply pre-configured HVAC setup. You select zones, you go to the air side system details, you assign the AHU or the terminal unit, whichever is currently applicable. You select the air system type, and then if there are terminal systems, you assign among the list of terminal systems available in our software library, and then go on proceed with the setup. So you can enter your input parameters as required, or you can just even use the defaults, which are based on ASHRAE recommendations. Even you can assign the chiller or the heating plant which is available within the library as the plant side system, and then go on to basically even configure the plant side system. You can assign the air handling unit supply fan parameters for the energy modeling, and you can change the parameters for the plant side also, which you are currently using in the current simulation. If you are using a heating system, you can modify the boiler parameters, you can modify the pump parameters, and for if you are using basically a cooling system, the chiller parameters. And then this is how, once you set up or assign those to all the zones, you can submit the configuration, which means the current HVAC system is assigned to the list of zones that are currently used. This is how the workflow is present currently, a very user-friendly workflow for a pre-configured HVAC system. If we go on to the next set of slides now, I showed you the workflow. Now I want to show the list of standard templates that are available in our library. So we have 4 plant side systems. We have the air handling units, both constant air volume as well as variable air volume. And we have terminal units, which are individual units, which you can assign to single or multiple zones as well. One by one, we'll walk through all of these and give you a glimpse of what they mean and what input parameters are basically required to set them up in the software. So the first one is the active chilled beam. So this is basically a terminal unit which you can assign to a zone or multiple zones, and you can provide both heating and cooling. In this, as we all know, is basically a high velocity primary air which induces the room using a beam coil. So the input parameters required for setting this up are chilled water temperature, the plant side temperature, basically those you can enter. Default values are always available. Flow rates, the air side primary air flow rate, supplied air temperature, the induction ratio, supply fan details, as well as control strategies. If applicable, you can basically input those in the panel. Then application wise, this can be typically used for showing annual energy consumption and peak demand reduction, sizing and optimization studies, green building studies, net zero energy target type of analysis, as well as lead projects. If you go into the software, I'll show quickly how it looks in the software basically. So if I go to within the panel now, as an example, I've selected one zone and I'm selecting basically a terminal unit for that zone, and I'm selecting the active chilled beam, which is available as a terminal unit. In that, you have options to set up the active chilled beam, basically cooling as well as the heating parameters of like supply temperature, heating and cooling supply temperature. And on the plant side, you can select whichever is applicable, either the heating plant or the chilled water plant. And once you go below, then you can configure the supply fan. Basically, if applicable, you can set up the supply fan details. And whichever plant side system you have selected, you can go and configure the plant side systems also, which is applicable. Let's say if you have selected the chilled water plant, you can modify the chiller parameters here, which are applicable. So there are default parameters which are available. You can even run with those because those are taken from ASHRAE recommendations, or you can basically enter your own values as if you have them. So this is how you set it up. Now going back to the next system is basically the passive chilled beam, which will be basically the same system, but the forced convection type of application is absent in that. So you don't have a forced convective fans which blow air. So this is sort of reduces the fan energy, and you can prove that using the simulations. In this, the input parameters are required that are cooling capacity, chilled water inlet outlet temperature similar to the passive active chilled beam, and water flow rate. A control strategy, if applicable, can also be specified. Next is the radiant panel, which is a simple, basically hot or cold water is circulated through panels which radiate heat to the room air. Then in that, if you select such a terminal unit, you have to select the inlet water temperature, flow rate, set points, and the heat transfer coefficients, which can be the radiative or convective or the overall heat transfer coefficients. Once you set it up, you can also use the default parameters as applicable. And in terms of application of this radiant panel, you can use it to show reduced fan energy consumption, optimize your design, as well as use it in combination of renewable energy systems that you are using and show peak load reduction as well. A very simple system that is also available in the library is the unit ventilator, which is basically a localized climate control unit in which there is by using an internal coil connected to a hot or chilled water plant that is available. And you can basically give ventilation also through this. So the parameters that are required to set this up in the software is basically the minimum ventilation flow rate, coil inlet water temperature, water flow rate, coil capacity, as well as the fan parameters. This can be used to study ventilation impact assessment for in the energy analysis, as well as study various distributed system performance scenarios. Unit heater is also available as a unit system in the library. This is basically a simple localized heating or a heater, which we call, which blows air, room air over a coil. So you can use hot water, steam, or gas or electric heating as a parameter in this system in the library, which is available. The input parameters that are required is heating coil parameters, inlet outlet temperature, flow rates, efficiency in case you are using electric unit, and fan flow rate as well as fan power. And you can use this for individual zones in combination with central systems and study basically partially conditioned spaces as well. Going ahead, we are going to see the chilled water air handling unit, which is basically a centralized air handling unit with ducts, which are commonly used for whole building performance, large commercial buildings, which will have central air handling units and a chiller side water plant to cool the air. Then this it is basically involves ducted systems mainly to distribute air to conditioned space, and it will involve all complexities like cooling coil, supply fan, filters, dampers, along with the AHU unit. So the input parameters also are basically more for such systems. You have to specify whether it's a constant air or a variable, which we'll study in the next slide. Then we also have chilled water capacity, which is many times auto-sized using the backend data in our software. Then we have supply air flow rate, fan power efficiency, as well as outdoor air ventilation per person, which as you specified. Typical application for this is the whole building performance simulation, as well as centralized cooling performance analysis. Similar to the constant air volume system, there is also a variable air volume system, in which basically the air, each zone, based on the zone heat load, there is a modulation of the adjusted supply. So there is modulation of the flow rate, and this is again a centralized cooling system, which has a plant side setup also. So in here, along similar to the CAV, you have to also give all those parameters that are applicable to CAV, but along with that, we have to give the VAV terminal details also, as well as the range or the minimum maximum airflow rate. You can use this system or this particular unit for zone level variation control. Again, whole building performance, central plant simulation, and advanced basically simulations which demand ventilation or load-based demand ventilation and occupancy scheduling. We also have split air handling units, both the CAV as well as the VAV type. And here, basically, these are simple systems which you can apply to individual zones. And here, the input parameters required are fan air flow rate, coil capacity, temperature set points, fan power efficiency. And these are often used as baseline for ASHRAE 90.1 studies. Going ahead, similar to the split air handling unit CAV, we also have the VAV type of unit. Again, in this, instead of a fixed flow rate, you give the fan air flow rate range, basically, which is different than the CAV system. You can use this in applications where part load operations are to be modeled, zone responsive cooling, as well as retrofit analysis. Now we have seen the air side systems. We also will see the basically the outdoor, the chiller water plant type systems, as well as the heater plant system. So here, this is the central cooling system with chilled water from chiller plants, and it basically circulates over the chilled water over the coils, and it basically cools the air in the air handling unit. Typically used in large HVAC systems. Here we have to give all the outdoor parameter details like chiller capacity, efficiency, chiller water intake, leaving temperature, pump parameters for the chilled water loop, condenser water loop parameters, and pump efficiency parameters for that as well. So it's a very detailed analysis for chiller, outdoor air chiller, which can be done. So you have to set up the plant side systems in this. All the details, like I showed, are available in the if you go to the software. This is where in the plant side you set all these details for the chiller as well as the heating water plant. Similar to this, so we expect this to be used for whole building performance simulation, lead ECBC, as well as other energy code compliance for entire building setup. So this is a detailed chilled water plant. Similar to this, we also have hot water plants. And again, this is the same. Instead of the chiller, we have a boiler, and we have to basically set up the boiler parameters. Rest of the application of basically circulating the heated water through heating coils, like within the air handling units, remains the same. Again, along with the entire circuit details, here the boiler capacity and efficiency are additional parameters that you need to define. And similar to the chiller plant, this is basically for cold weather region. Similar type of analysis for large buildings, schools, hospital, office buildings, and lead ASHRAE compliance studies can be done using this. So I think for rest of the systems which are there for air handling, I will hand over to my colleague Aditya, who will walk you through the rest of the systems. If you have any questions on already explained systems, you can always ask them in the chat at the end of the webinar. You are always welcome to even email us for any details. So thank you for your attention and interest. So Aditya will carry forward rest of the unit systems.
Yeah. Thank you, Swapnil, for passing over to me. Okay. So next set of systems are the next system is variable refrigerant flow. So as the name suggests, it transfers heat from using flow of refrigerants. Basically, it is mostly used when your thermal loads are diverse and you need different temperature controls in different spaces or different zones. So basically, it works like it has a one outdoor unit which can be connected to multiple indoor units. And like you see in the diagram, the refrigerant flows from outdoor unit to each indoor unit, and based on needs of thermal needs, the flow of refrigerant changes. So basically this system is installed where space limitation is there, where uh, the uh, the energy efficient systems are needed, there the system is used. So in buildings here, if you see the must to have inputs are you have to, if you choose for VRF, you have to connect it to VRF condenser loop as Swapnil has showed. You have to go into the plant section and then need to define variable refrigerant flow condenser, provide parameters. As of now, in this standard template, you can only change meta properties and define this condenser loop and then connect it to your air set system. So in the cooling and heating system, DX coil is being used. You have to provide what will be the expected supply air temperature for heating as well as cooling. You have to provide supply fan properties like pressure, efficiency, zone static pressure, etc. And if outdoor air or ventilation its requirement is there or it is designed, you can just tick mark yes, and then it will be considered for simulation. So basically, application is it is being used for the projects which is large commercial spaces, hotels, schools, or if you can see hotels or hospitals where each room needs a different temperature, there it is being used. So basically, it is very efficient systems and easy to install and easier to retrofit. So yeah, I think Praveen, you can shift to the next slide. Yeah. So next is 4-pipe fan coil unit. As how this distinguishes is 4-pipe fan coil unit. As earlier in VRF system, it was using refrigerant as a media to transfer heat from indoor to outdoor. Here it uses water as a transferring media from the chillers and boilers. So in this 4-pipe fan coil unit, as it name suggests, hot water and chilled water is being used. You have to connect your 4-pipe fan coil unit with plant connection. Like you have to define chilled water loop and hot water loop in the back end. Cooling and heating supply temperature, you have to provide fan properties, and if outdoor air is there, you need to provide. Basically, these systems, this is a very good system if when you have to maintain your humidity and temperature precisely, as it can provide heating and cooling simultaneously in different parts of the building, as well as simultaneously it can provide heating and cooling. So as it is using separate pipes for heating as well as cooling, unlike 2-pipe fan coil unit. Yeah. So yeah, so for precise temperature and humidity control, you have to use this system. So you can define this in buildings here as well. Yes. So next set of system is water source heat pump, which is very efficient. I'll say it's like most efficient heat pump system because it uses water as a heat sink or heat source. Because of it, it can maintain stable temperature on the outdoor unit side, which gives its capacity to that it's very efficient. So it is mostly used for the buildings or projects which are located near the lakes or rivers or large water bodies, where this system uses outside water as a heat source for heating, and for cooling it uses water as a heat sink. So in the our system buildings here, you have to define the first condenser loop and connect it to water source heat pump, which is under category of terminal unit, and all other parameters like supply temperature and fan properties and outdoor that you need to define. Yeah. So this is the most energy efficient system that you can use. It's recommended by ASHE. So after water source heat pump, the next set of terminal systems are PTAC, that is packed terminal air condition. As name suggests, it is self-contained system in which it is all the indoor as well as outdoor. Unlike other system which has indoor and outdoor units are separate, it has both units which are self-contained in one package only. Because of it, it is very easy to install and easy to retrofit, and that's why it is being used for retrofit as well as where your space is limited or where space constraints are there, where it is being used. So like apartments, hotels, it is being used. So this packed terminal air condition, compressor, evaporator, condenser, all will be all components are there in the only one packet, which is packaged. And typically for heating, it sometimes if it based on model, it also has a heating mode which uses electric resistance coil for the heating. So yeah. So for this, as this is a terminal unit and which don't use separate plant or something like, you don't have to provide plant like other systems. You just have to provide cooling, supply temperature, heating, supply temperature, and choose the source as an electric resistance and fan properties and outdoor air units. So this is the thing. And if you are looking for cost-effective solution, then selection of the system is good. Like packaged terminal air condition, this is also similar on the similar line. Packaged terminal heat pump. It is a heat pump which is packaged in the one box. I'll say, which is self-contained. All the compressor, condenser, evaporator, all things in one packet. Because of this is also very good for retrofitting application as well as where space is constrained. So how heat pump works? It basically works on the principle of heat pump. It uses reversing wall switches, which reverses fluid flow. Like in the winter, flow is different, and in summer it reverses flow. So that heat in winter, heat from outside to inside it is transferred, and in summer heat is extracted from indoor and sent to outdoor. So yeah. Yes, Praveen, you can change this slide. So those are about air systems. Now coming to condenser loop. So as Swapnil had shown, there are two sections: air side system section and plant side section. Condenser loop is mostly used for larger project where cooling using air cooled or air cooled chiller are hard to use. And you basically need or maintain consistent cooling performance, or and when ambient temperature is very high and it is hard to transfer heat in the air, so then water cooled condenser are used. So it is basically robust systems. So it cannot be directly attached to your air systems, but for your chilled water chillers as well as for your DRF loops, you have to use condenser if you are choosing for water type cooling. So input parameters are you have to define your pump parameters like pressure rise, flow type, which is a variable or constant speed, and flow control. Is it a continuous or intermittent? Cooling torque, you have to define the specifications of cooling tower. The fan type is variable or constant. What is the supply temperature, approach temperature, what is the range, and what is the capacity of your cooling tower. So that's it. Application is, it is employed in very large offices, very large commercial spaces, malls, as well as supermarkets, where very large indoor load is there, and it is hard to extract that heat or from the indoor space. It is a robust design because it uses water for the evaporation. Water evaporates and the cooling effect is getting generated. Then it comes to variable refrigerant flow loop. As we saw condenser loop, here also in a variable refrigerant flow loop, you have to connect it to condenser loop. As basically this variable refrigerant flow loop, it is used for VRF system. As we have seen in air side system, there was a VRF system. There you have to choose this system, as this VRF loop is nothing but the loop which transfer heat from the outdoor unit to the multiple indoor units, and then from this VRF loop, it can be transferred to cooling tower using condensers if it is water. So because that's why in input parameters, condenser type, you have to choose whether it is air cooled or water cooled, and if it is water cooled, you have to again define condenser loop and provide specification. So basically this VRF system, as earlier suggested, where space is constrained, retrofitting is needed, and where diverse zoning needs are there, like if each space or each zone has a different temperature requirements, there you can use this VRF systems. So as we have gone through all the air side system we have currently available in buildings here. So basically we cover most of the HVAC system which are required for ASHE 90.1 baseline HVAC system. So you can come up with your model, upload your building model. We have all the materials required for ASHE 90.1 compliance. So you can define your building model accurately. And then in HVAC system, we have most of the HVAC system that are covered in ASHE 90.1, so that you can do energy simulation, which is baseline compliant. So you can see whether your load and energy calculation is it compliant to baseline or not. So yeah, so basically this covers, and in the next quarter we are coming. So currently we are only allowing users to change meta properties of the system. So these are predefined HVAC system. All the components are predefined. You can only change the properties here. But in the upcoming quarter, we are currently developing a feature which will have a canvas in which you can add new components. You can create your custom HVAC system. You can change properties as well as you can add or remove components to come up with basically the HVAC system which caters to your need. So that we are coming up with. So it is very interesting to work on this project. So currently feature we are working. Along with this, AI integrations are going to come, so that will make our application more and more user friendly to come up with so that you can define your HVAC systems, you can define your building models very easily, and it should not, the process will not be time consuming. Yeah, can pass.
Thanks, Aditya. So as Aditya mentioned, this is at the early stage, and we are in a continuous product development cycle. So for HVAC configurator, we are bringing in this detailed custom layout, HVAC layout canvas in the next release. So meanwhile, if you how you can contribute or you can access this, like we are providing early access of this Buildings AI platform. So you can go to our website, request a demo of our app, schedule a call with Swapnil, and then you can discuss more of your requirement. We can understand your requirement. It will be a discovery call, and then at the end of the call, we'll provide you with the early access, so you can access the it's limited, it's a private beta kind of thing, so you can uh, experience the software yourself and in your current live projects, and you can give us the feedback, raise request for some new features, so we'll work on it, and we'll be able to deliver it to you, like add it to the software. So yeah, that's it. So now the session is open for Q&A. So let me stop sharing, and yeah, let me see the questions. Okay. So there was one question about from Varun. Can we do MEP HVAC modeling as well in the same software, or we use a model for calculations only? So if I understand the question rightly, like this is the heat load calculation and energy analysis platform. The modeling of MEP, like the HVAC model, the 1D model can be done for calculation, but not the the modeling of the ducts or the mechanical. If that is a question, I hope it answers it. And then
Praveen, I think I'll be very happy to connect with Varun to understand his needs.
yes, yes.
So I think we can see if we can connect somewhere somehow and discuss the requirement. So in the long term,
Sure.
we are developing whole building performance simulation. So not in the latest releases, but yeah, requirement is there that we should have MEP designing also in the platform, but we'll
Yes,
need
that's
more and
the
more feedbacks or vocal data from users like you.
right, right. Well said. That's the forward direction. Yes. So there was one question about the air movement happening in passive cooling system. Swapnil, would you like to answer that?
Yes, I already posted in the chat box also. So air movement in passive chilled beam is basically natural convection current dominated. So these like are mounted ceiling mounted units, and typically like the heated air or the warm air rises. It comes in contact with the chilled beam. The temperature drops, and again due to the natural convection buoyancy effects, it comes down. So, but this particular units are basically only suitable for I would say moderate climate or moderate warm type of environment.
Okay,
Although there
okay,
is
thank you.
savings of fan energy, but like this is probably the application is limited to moderate climate.
Okay, okay, great. So there is another question from Ajit Nair. Is there any template for modeling the regular split air conditioning system and demand control ventilation systems? Yes, Swapnil, I guess you have already answered on the chat box, but maybe for the others it might be useful. Yeah.
So Ajit, split air conditioning systems can be modeled in the current version. Demand control ventilation systems, I think currently it can be modeled, but not through UI. So basically we are using Energy Plus in the backend. So we'll be able to do just I think we'll need to develop this thing. So we'll need to bring this to UI. So I just post if you need any other HVAC system which are not available in the current system, just write it to us. We can easily bring that to front. So currently UI we have limited because it should not be very complex. As currently softwares which are in market, we are that we have observed that those are not very user friendly. So we are trying to keep it very user friendly. So currently it is not, but from backend with support of our development team, you can write a support request and we are able to model any system that is possible using Energy Plus. It just will need some development support.
Okay. So, and a connected question was, are there any components in buildings AI for optimization, like parametric optimization and to understand the energy consumption? For example, varying airflow, varying
Yeah,
size.
so parametric studies can be done. So we have a very, through the UI, we can easily copy any project and any configuration, HVAC configuration, create multiple copies of them, change the parameters and manually set up parametric runs. All can be done together. Like all, let's say you have 10 copies and 10 different configurations. You can run all the 10 together. But right now, the tool does not support automated parametric solver. So it's not, so you have to manually compare those results. There is no, I would say, simultaneous viewing of results of all parametric runs together. We are working on that, but currently it's manual parametric process, optimization process.
Okay. So one more question from Mr. Pandurang. So this AI HVAC can do the drawings and calculation and estimates. So I'll clarify a little bit, so there are different AI agent workflows, keeping human in loop at different stages of the workflow. So yes, it does the calculation and estimates of heat load calculation. So for example, one interesting AI agent workflow is PDF to BIM that we are working on. So which is, converting the, right now you can directly import the AutoCAD architecture drawing file into, into our software and convert it to BIM and directly start working on it. And then we are bringing up PDF to BIM. So your drawing file is converted to PDF and the AI will detect all the objects, walls and the measurement and everything, it converts that PDF file into usable BIM, building information model. And then, use the all the details. For example, it reads the space name in the drawing or the PDF file and assigns the schedules according to the space type as per the standard. So these AI agentic workflows are being included, added in the. So we also conducted another webinar where in detail we have shown all the features, those features as well. We'll email you those webinar links as well, the previous webinars as well. So it will be interesting for you to look at the other features as well. Okay. We'll take few more questions and then in this. So I can see from Mike, how do I assign HVAC system to specific zones? Aditya?
Basically, as okay, I'll open my project. Screen. Okay, is my screen visible?
Yes, yes.
So like you can see, so I can come up with a building model while creating the HVAC system. You have to choose your building model, and then this HVAC configuration tool, it fetches all the zones you have modeled in from the building model or available in your BIM model. Like you can see here, these are the zones. So if you have to provide HVAC system for a single zone, I just have to create one HVAC system. I'm just going by defaults as of now. I have to provide all the required parameters and save this HVAC system. So once this HVAC air side system is created, so you just have to go here and choose air side system. So this is how you can assign to one single zone, and if you wanted to do multiple, you can assign to multiple zones as well. So just go here, assign this, and you can assign your zones with the air systems. And next thing is, like you can see in the center coding, you can assign your air side system with the plants here from here, and define plants from here. That's it. I hope it is clear to you. If not, I think we can have a demo session separately. So
Okay,
that
great.
so we can train you guys to use this software.
Okay. So one more question from Khaled. Can I run multiple HVAC simulations simultaneously? And how can I ensure compliance with energy efficiency standards? Like, yeah, two different questions. Yeah, from the same person. So first one, how can I run?
You would like to
Can I
answer
run
me?
multiple? Yes, you can.
So, sorry to interrupt. Some comment is there where current discussion screen not visible is there. Can you check what the issue is?
The share screen probably it was not visible, is it? Like I was able to see, but maybe we'll connect, separately and share this. Like when we send the recording of this webinar, we'll get all the details. That will. So can you provide previous webinars tutorials available, post them on YouTube? Yes, Ajit will be sending the current webinar as well as the previous webinars list. You can already find our previous webinar on our website. Yeah, we'll send you the email link in the email.
I think
question.
one more question is there.
I think coming to question about HVAC systems, can multiple HVAC simulations can be done in simultaneously? Yes. So as this is a cloud platform, you can run as much as simulations at a single instance. So there is no problem running multiple projects, as well as we'll be opening this platform for the collaboration mode as well, so that your team, different members of your team should be able to run simulation, as well as you can edit or you can view your projects as well. So collaboration feature will be there. You'll not find it in the early access, but if you have any need, so then just let us know. I think it is designed in that way. We can easily bring this forward.
Yes. I guess we are almost at the end of this. So rest of the questions we'll connect with you separately, individually, and then answer those. So as thanks for joining the webinar and asking, making it an interactive session, posting more questions. Thanks for it. And Swapnil and me will be, connecting with everyone and try to onboard you on the early access program. So looking forward to, the collaboration. Thanks. Thanks everyone. Thanks Swapnil and Aditya.
Thank you all. I appreciate your time. Thank you.
Yes, thank you. Yeah, have a nice day or night.